Today's the day we put everything together from the last few sections. So we're going to be putting together what we know about first derivatives and second derivatives, as well as previous learning about x-intercepts, y-intercepts, all that good stuff, and using that information to sketch curves. So we'll review kind of all the characteristics you've done since Algebra 2 through to current. All right, with special emphasis being on the relative extrema, increasing, decreasing, concave up and concave down, and inflection points. So each of these pieces of information tells us something about the others. So if we know f of x, we can conclude things about f prime of x and f double prime of x. So if we know that the function is increasing, then we know that f prime of x is greater than 0. We can't conclude anything about the second derivative just based on the fact that it's increasing, so we put just no conclusion there. F prime of x is less than 0, our rate of change is less than 0 when we're decreasing. Once again, we can't conclude anything about our second derivative just knowing about the slope of the original function. When we're constant, that means f prime of x is equal to 0, right? And we, once again, can't conclude anything about the second derivative. But when f prime of x equals 0, right, we have a critical point. So a candidate for max or min. Concave up doesn't necessarily tell us about our first derivative, except unless there's a point, a relative min, or so concave up, that would mean if it's positive, or yeah, but no conclusion. I'm getting ahead of myself. All right, so concave up means our second derivative is greater than 0. And if we're talking about when our first derivative equals 0 at a critical point and our second derivative is positive, then we have a relative min. Right? For concave down, our second derivative is negative. Right? If f prime is equal to 0, I should have put that there, and f double prime is less than 0, we've got a relative max. Right. So those are some conclusions we can draw based on the original function. So let's look at this original function and think about what we've got going on here. So we can think about our first derivative and our second derivative by looking at this graph. So the first derivative equals 0 at critical points, or when our tangent line to the function equals 0. That occurs at 3 points on this graph, at -4, at -2, and at 1. Each of those places has a tangent line with a slope of 0. And then we look at it and we say, what's happening to the left of -4? Well, we're increasing. Just write inc. And then after that, we're decreasing until -2, and then we're increasing again, and then we're decreasing. So this tells us that our first derivative is going to be positive, negative, positive, negative. Right, and then let's think about the second derivative. So for this, we're thinking about concavity. So if we're looking at this piece here, that's going to be concave down. So we're concave down until that inflection point at -3. And then we're concave up until this next inflection point at -1, +3. So that would be at -1. And then we're concave down everywhere after that. So let's write that. We've got negative when we're concave down, positive when we're concave up, and negative when we're concave down. So this is C down, C up, C down. We can use that information now to sketch a graph of our derivative. So now our x-axis, instead of being y value, our y-axis instead of being y values is going to be our derivative. So we know our derivative is 0 at -4, -2, and 1. Our other important points being at -3 and at -1. So we know that it's increasing, or that we have a positive positive derivative to the left of -4. So we should be up top to the left of -4. And then we have a positive, we have a negative first derivative between -4 and -2. So we should be down here somewhere. We switch to concave down to concave up. So this is where our second derivative equals 0. We're thinking about our second derivative as the slope of our first derivative graph. So we've got a slope of 0 here, and it switches to concave up until -1. So we go back to increasing. At -2, we've got f prime, our first derivative, equal to 0. And then at -1, we switch to going back down because our second derivative is going to switch to negative. Right? And we're positive y values, positive first derivative until 1. So -1, we switch from going up to going down. And then we're positive until we get to 1. So we've got a first derivative graph that looks something like that. All right. And then our second derivative graph, we need to have negative y values to the left of -3 and positive y values between -3 and -1, and negative afterward. So we're going to have something like that. All right, so that was a lot. We're going to play with these concepts a lot more, but now we're going to look at what we can conclude based on our first derivative graph. So our first derivative graph, if we are equal to 0 or undefined, we are going to have a critical point on our original graph. And our second derivative, if f prime is undefined, then our second derivative is also undefined. Right. If f prime equals 0, then we're going to have some value of the second derivative. We don't know enough to conclude anything about it. So we will have a value, so it will be defined. If we've got a second derivative greater than 0, we are increasing. That alone doesn't give us enough information to conclude anything about our second derivative. F prime is less than 0. We are decreasing on our original graph. And that doesn't give us enough information to conclude anything about our second derivative. Our first derivative changes from positive to negative. So if we go from increasing to decreasing, so it goes from increasing to decreasing, that's going to give us a relative max. And then at a relative max, right, f prime equal to 0, we know that our second derivative, that at a relative max, it's going to be concave down, right? So our second derivative has to be less than 0. Changes from negative to positive, we go from decreasing to increasing. So that's going to be a relative min. And we've got a relative min, so that means our f prime is going to be equal to 0, and our second derivative is going to be greater than 0 because it has to be concave up at that point. Lastly, we're going to look at the slope of the derivative graph. So remember, the slope of f prime tells us about f double prime, or our second derivative. So if the slope is increasing, that's going to tell us that our second derivative is going to be positive. And if our second derivative is positive, that tells us that our original graph is concave up. And our second situation here, we're going to have concave down. If I can spell, yikes. Concave down, and our second derivative will be negative. And that's consistent with our definition of concave up and concave down, because as we have concave up, our slope is increasing, and as we have concave down, our slope is decreasing of that original function. So here we've got f prime, and we're going to make some conclusions about f double prime as well. Well, I should do f prime, f double prime. So now that we're looking at the first derivative graph, we have a situation where we're a little bit different. So when we look at this, our x-intercepts are going to be where our first derivative equals 0. So where does that occur? Well, that occurs at -2, 1, and 3. And if we look at our y values, or our f prime values, we are negative to the left of -2, positive between -2 and 1, negative between 1 and 3, and positive afterward. So that's going to tell me that my original graph until -2 is decreasing because my first derivative is negative. And then I'm increasing between -2 and 1 because my first derivative is positive. I'm decreasing between 1 and 3 because my first derivative is negative. And then I'm increasing from 3 all the way to the right because my first derivative is positive. Then our second derivative, this is going to be the slope of f prime. So we're looking for where the slope changes from positive to negative. That happens at -1 and -2 and 2. Yeah, -1 and 2. And we go from positive to negative to positive. So that tells us that our original function, I should have made my number line bigger for my original function, but my original function, since the second derivative is positive, is concave up to the left of -1, concave down from -1 to 2, and then concave up after 2. So let's construct our graphs based on this information. So if I'm doing the graph of f, I've got important things going on at -2, -1, 1, 2, and 3. So I'm concave up until -1. So, and I have a relative min at -2 because I switch from decreasing to increasing. So we don't have an indication about the y values. So there's going to be multiple representations that are correct for this. Okay, but I'm concave up until -1, and I'm decreasing until -2, and then increasing from -2 to 1. So I'm still going to be increasing after this, but we're now concave down until we get to 1. So arched, so I'm concave down. And I'm still concave down until I get to 2. And I'm decreasing all the way until I get to 3. So I'm concave down to 2. And then I switch to concave up, but I'm still decreasing until I get to 3. And I'm still concave up after 3, and now I'm increasing. So my function should look like this. You could have higher peaks or deeper troughs. That doesn't matter, right? Because we don't have any information about that stuff. So this is f of x. And then if we look at f double prime, we have positive values. So left of -1, negative until 2. So f double prime has to look like that. I recognize that this is all a lot for you guys, so we are going to take a few days to just practice with this. Right. We also have office hours coming up, which I will message you all about. So now if we're looking at the second derivative graph, right, we can draw some conclusions. All right, so let's think about each of these attributes for our second derivative graph and what they tell us about a function. So when we have f double prime equal to 0, that means our original function is potentially going to have an inflection point there. Right. And then if our second derivative is undefined, then f prime is got to be undefined. Right. F could also be undefined. Doesn't have to be, but it could be. Right. So if f double prime is undefined, then the first derivative is also undefined. All right, and at equal to 0, we have a potential inflection point, but we can't draw any conclusions about the first derivative at that point. our second derivative is positive, our original function is going to be concave up. All right. And then if our first derivative is equal to 0, and this should go in this box, sorry. If our first derivative equal to 0, then we'll have a relative min. Because remember, concave up and first derivative equal to 0 is a relative min. First derivative, we can't really draw conclusions about just based on the second derivative graph. Well, is that quite right? I have to think about that for a second. So I have to go back and edit this a little bit. So if f double prime changes sign, at this point, then f prime will have a relative min or max. All right, and then our conclusions based on concavity. If f double prime is no, we don't need that. Oh, I'm getting ahead of myself. I'm sorry, guys. This part goes down here. All right, so f double prime changes from positive to negative would mean we go from increasing to decreasing. So that means we're going to have a relative max on our f prime graph, relative min on our f prime graph. All right. Sorry I flubbed this one up, guys. If our second derivative changes from positive to negative, that means we have an inflection point where we change from concave up to concave down. And then this is inflection where the opposite happens. All right, last graph to draw conclusions about. So we've got f prime, f double prime. So f double prime is 0 at 0 and at 3, and it's negative to the left of 0, positive to the right of 0, and positive to the right of 3. So what does that tell me about my original graph? Well, if I'm thinking about 0 and 3, I'm going to have concave down and concave up. Since the second derivative is the slope of the first derivative graph, then we know we're decreasing here, and then we're positive, so we're increasing. All right. other conclusions we can make when our f prime graph changes from decreasing to increasing. This is going to be a relative min on that graph, and then the increasing to increasing is nothing on that graph. Right. What else can we make for conclusions? Okay, so that's our conclusions that we can make about the graph f. And then those are the conclusions we can make about the graph f prime as well. So we don't really know about positive and negative values for each of those. So sketching a graph, we could get a number of answers, right? But we can't conclude about increasing and decreasing for the first function. So all we know is that it's going to be concave up until 0, and then concave down until 0, and then concave up. So we know that it has a shape that looks like that, but we don't know. And then it's still concave up after. So we know that f has to have a shape that looks like that, but we can't really say anything more than that. And then for f prime, we've got decreasing, increasing, decreasing. So we know that it's got to be going down. Then we know that it's got to be going up, and then it's going to be going up again. Right, but we can't really draw more conclusions than that. So for these ones, we'd just be able to talk about those characteristics I've listed. We can't really make the graphs. Right, we're going to dig into more examples later in class and as we go. So for now, this is your notes. And then you're going to try... Oh, yeah, you're going to try... this problem and this problem and this problem, all right? And if you have questions, we can talk about them in class.